This is a Kenwood Model 500. This is very closely related to the Kenwood 600 and 650. They are all a part of the Kenwood Supreme series. Someone brought this amplifier in with occasional channel dropouts. I'm going to cover what you need to do to restore the amplifier section of this amp, and then I'm going to go over how to safely boot virtually any vintage amplifier. One of the most important things you need to do on a Kenwood Supreme series amp is go after power supply B board. This board needs to be restored. It's typically in bad shape. The solder joints are typically very cracked because these power transistors run hot. You need to replace all the capacitors with 105-degree caps. As always with any vintage circuit board, test every single component in circuit. If something looks wonky in circuit, pull it and test it out of circuit. The next thing you need to do is you need to go after the power amp board. This is akin to a driver board. You need to replace the old carbon element potentiometers. Specifically, if you are adjusting an old carbon element bias pot, and if that bias pot goes open, you don't have an amplifier. And when you don't have bias, you can severely damage an amplifier depending on the circuit design. Replace the caps. There's only 4 in. Very definitely test these transistors right here. These are often problematic in Kenwoods. On this amplifier, they tested great. To get at this board, it takes a lot of work. It's not easy. You've got to get the heatsink out of the way. You've got to fold down the back to be able to service this board, to be able to get to the rear trace side. While this back is folded down, you want to clean the normal separate switch and the phono impedance switch. Test your filter caps with an ESR meter. Look at the condition of them. Make your own decision. Clean up the switches. There are a number of wafer switches in here. The brass gets black oxidized. Clean that oxidation off. Clean all your pots. Clean all your toggle switches. One of the most important things you need to do on any vintage amp is you need to pull the output transistors and test them. They can be surprisingly on the way out and you won't even know it until a dramatic failure. The benefit is that you are going to clean up all the old dried up thermal grease and apply new thermal grease. The new thermal grease will be a lot more effective at heat dissipation. After you've done all this, you've got a good idea of the condition of this amplifier. Now you can make a decision as to whether it's ready to be booted up or not. I use a very safe method of booting up any vintage amp. First, I use a dim light bulb. The dim light bulb allows us to take a look and see if there's any shorts in the amplifier, because if the light bulb glows brightly, that means we're drawing a lot of current. That means there is a short. Additionally, the resistance of the filament limits the current to the amp, and that in turn makes it very difficult to really damage an amplifier. I also watch my amp meter, and I also watch my bias. Bias spec on this amp is 25 millivolts. I like to sort of track into 25 millivolts or less. However, a little bit more is perfectly fine because the bias will drop a little bit when the amplifier warms up. You must be prepared if you see the amp meter go sky high or the dim light bulb go bright to get out of the Variac job immediately. Just shut your Variac off. Don't even ask questions. Now, if the amp meter has gone sky high, you definitely have a shorted condition. You're going to have to go back through your amplifier and find out what's wrong before you even attempt another boot up. So here we go. We're going to boot it up. And the first thing we're going to notice is we're going to notice a ramp up in the bias, because the bias is going to start conducting. There's our ramp up. Next thing you're going to see is a filament glow on our dim light bulb. The light from the light bulb is going to be brighter on the camera than it really is in real life because of the camera exposure. There's our filament glow. That's to be expected at this stage. Right now we're at 90 volts. Now the next step is to listen for the relay. It's about 4 feet away. The light bulb will glow more brightly when the filament shows the brighter glow. That's about when the relay is going to click in. There we go. There's our relay engagement, and we're approaching 120 volts. We're watching the bias, we're watching our amp meter, and we're watching the glow of the lamp, and the glow of the lamp is very appropriate. There's nothing wrong. So we've proved one thing right now. We have proved that there's no shorts in the amplifier. I don't see any evidence of that at all. Our bias looks good, 20, 22.6. Bias will actually go up when we remove the dim light bulb from the circuit. It's okay to be a little bit above spec. Be perfectly fine to be a little bit above 25 millivolts because it will drop when the amplifier starts to warm up. So we're out of that step, and now we're going to boot up the amplifier without the dim light bulb in place. By the way, you've got to wear gloves when you do this work. Wear double gloves. I do all the time. So we're going to go up. Be ready to get out immediately if you see the amp meter jump up. The reason why I wear double gloves is that also you have a layer of air between each glove, and air is one of the best insulators. There's our ramp up. Now we can watch our amp meter closely, and I see no evidence of shorting in this amplifier at all. There's our relay. Some amps will jump a amp meter when the relay engages. That's why I like to operate my meter on the high setting. I like to take care of my meter. I don't want to see them get jammed. And we're approaching 120, and everything is perfectly A-OK. Our bias looks good. It's slightly above the 25. That's perfectly okay. It will drop as the amplifier warms up. Now we're going to adjust DC offset. You might ask, what is DC offset? And a professor of mine once said in electrical engineering, he said, you're not going to really understand this class until you take the next class. And that's the way it goes in engineering. So to understand DC offset, you're going to have to understand an AC signal. An AC signal contains information. We compare amplifiers from one amplifier to the other amplifier, and we put in a 1 kilohertz signal at 1 volt. That is the standard by which all manufacturers stick to, so we can compare one manufacturer's amplifier to another manufacturer's amplifier. So we've got a 1 kilohertz signal. That means 1000 hertz. We call it 1K for short. And a sine wave contains information. Why? Because a sine wave moves a woofer and or a tweeter in and out. And that movement of the tweeter or woofer in and out creates sound pressure, and we recognize that as music. DC, on the other hand, does not contain any information. It's just a flat line. It can be positive or it can be negative. Now, if we were to look at an orchestra playing on a oscilloscope display, we would see literally hundreds of frequencies all coalesced together, bouncing around on the oscilloscope display. But here we are, we're essentially playing a single frequency into our amplifier to get a good reading on our amplifier's health. You wouldn't want to sit around and listen to a 1K signal. It doesn't sound very good. So DC has no information. It does not move a driver. does not move a woofer. It does not move a tweeter. And if you put enough DC onto a speaker, it will burn out the voice coil. We want to minimize DC as much as possible, and that's why we do a DC offset adjustment. So here's our DC offset right now on this amplifier. I'm just going to show you one channel. I'm going to move it around a little bit, and we'll see how it can go into the positive, and we can see how it can go into the negative, and how we can get it very close to 0, which is the ideal. We always want to use an insulated screwdriver. Never try to use a metal shaft screwdriver in an amplifier while it's on. So I'm going to take the DC to the positive. So that spec right there, that would be perfectly okay, because the spec is plus or minus 20 millivolts or less. Notice how I said plus or minus. It can be even positive or negative. I'll show you negative in a moment. Centered around 0. We want to get as close to 0 as possible. I'm going to take it into the negative. Past 0. We've just gone past 0. We're going into the negative. And that would be basically an okay measurement right there. But we really want to get to the ideal. We want to get to 0. So we're going to go to 0. We're going to land at 0, as close to 0 as possible. It's a little, very sensitive adjustment, and for all practical purposes, we've arrived at 0 DC offset. Can't get much better than this. It will bounce around, okay, a little bit. There's nothing you can do about that. It's perfectly fine. Next thing we want to talk about is bias. Bias has indeed dropped a little bit. It will continue to drop as the amplifier warms up. And here's our bias. Has dropped. And I will adjust bias for you, so you get an idea of what that looks like. We're going to be looking at this display right here. I'm going to drop it. I'm going to go back up. And I'm going to put both of them at 24 point, in theory, 5. Okay, we like that. Back off a little bit. It's very, very touchy. I'm going to take the other one to the same match. You want to be matched, okay? .4. Okay, so that's how you adjust bias. So everything's going very well. We've done our boot up. Determine there's nothing wrong, inherently really wrong with the amplifier. Take a look at DC offset and bias. That went well. Now we're going to look at the frequency that we're putting into the amplifier is 1K, like I said before, and we're going to look at that on the oscilloscope. So I have to do some setup here. It takes a couple of minutes here to set everything up. Not even a couple of minutes. There's a lot going on here. You got to be very careful about hookups. You could really blow something. So we're going to be looking at an AC voltage on an oscilloscope, which is a sine wave, which is a very beautiful thing. So we want to set our meters here to AC, because we're going to be looking at a voltage measurement on our meters. When we bring it up to power, we're going to do a wattage calculation. Okay, so we're ready to look at the oscilloscope, and we're going to discuss a whole bunch of stuff on the oscilloscope. The sine wave is one of the most beautiful things in nature. There's a lot to learn about sine waves. Could be a whole entire, several university courses. Okay, so we're going to bring up the amplifier volume. Want to check, just double check, always double check your work, okay? Just double check your work. A lot going on with all this hookup. And we're going to bring up our volume and we're going to see the very beginnings of a sine wave. Now the thing we're looking for is equal amplitude in both channels. Now it'll never be exact, but we want to make sure that it's at least pretty close to equal. And by equal, I mean equal in amplitude, equal in voltage output. Okay, so the difference between the bottom and the top is our amplitude, and we want to see that to be equal in the left channel and the right channel. Now if we take a look at the oscilloscope, we can also take a look at the voltage output on our meters. And the left channel is producing 9.22 volts AC, and the right channel is producing 8.85. Now that's pretty close. That's normal. You'll never get it exact, okay? And it changes as you bring it up because of the volume compensation of the potentiometer. All kinds of stuff goes on. You'll never really get exact. I mean, if you want to buy a very expensive volume control, it'll be more accurate. Like, for example, a stepped attenuator that's hundreds, if not thousands of dollars, will be way more accurate than an old potentiometer from the 70s. Okay, so we're going to go up and we're going to talk about distortion. We don't see any distortion. There's no distortion here. You may have heard of crossover distortion. Crossover distortion, again, as we go above the zero line and below the zero line, we've got a midpoint, and the midpoint is right here. The crossover from the positive down to the negative is right there, and if we see a wiggle, a distortion, an aberration right there, that's called crossover distortion. We don't see any evidence of that on this sine wave. It looks beautiful. It's a beautiful, nicely formed S-curve. Now, I've taken a look at all these signals here, and they look great. There's no distortion. I feel more confident that we can take this amplifier up to power. What do I mean by up to power? We're going to take it up to just before clipping. Now, I do want to show you clipping because we want to have equal symmetry in clipping. Now, clipping means just that. We clip off the top and the bottom of the sine wave, and we want to see an equally sized flat top and flat bottom on both channels. So I'll show you that briefly. We don't want to hang out there too long, but I will show it to you. And there's our clipping, and it's symmetrical. It's a beautiful thing, okay? Then we back off. We don't want to hang out there too long. It's okay to look at these waveforms. I want to make that clear. You've got to test your amplifier at power. If the amplifier cannot make power, there's something wrong, probably in the output transistors, maybe in the driver stage. So we're going to go all the way up to just before clipping, and there's a little variability in this, okay? You got to understand that. It's not perfect. So we're just before clipping. We're going to take a look at our meters here. We're at 31 volts. That's a nice match. 31.75, 30.98, etc. Okay, so that's good. We're going to take it down in power. We don't want to hang out there too long. We don't want to go to lunch. We don't want to heat up our load resistors too much. And now we're going to calculate power. So just to give you some rough ideas here, it all depends on where we measure and how hard we want to push to just before clipping. But let's say, for example, we had 30 volts. 30 volts squared divided by our 8 ohm load resistor equals 112 watts. And that's a good average of where we were sort of looking at. And guess what? The specification on the Kenwood 500 model is 110 watts into 8 ohms at 1 kilohertz. So we nailed our power spec. Dead on. 112 watts. So that gives you an idea of what to do with a vintage amplifier in terms of rebuilding everything. Okay? Don't ever forget about the power supply B-board. It's the easiest thing you can do on this amplifier. Just unscrew this screw and it pops out. It gets a little more difficult, quite a bit more difficult. when you got to take the heatsink apart and all that area to get at the power amp board, but I've done several of these. I want to drive home one of the most important points of this whole discussion is that, again, you need to be very careful about booting up a vintage amplifier. This is a real-life story that happened to me not too long ago. This is a driver card. In Sansui world, we call it a driver card from a Sansui 9090 DB. And this is also a driver card. Kenwood just calls them power amps, which they are. They're a power amp. And there are two channels on this driver card. There's a left and a right. You can kind of see the symmetry. And I've been working on this amplifier for like a long time. Days and days. And all of a sudden, I'm variacing it up. I could have just like turned it on because I was getting confident with it. But I said, oh, I'll just keep using the variac. I saw my amp meter go to the moon. And I'm like, okay. So I shut it off immediately without even hesitation. I removed the driver card from the amplifier. It's okay in the world to boot up a Sansui 9090 dB without the driver card in place. And there was no amp draw without the driver card. So I knew at that point that it must be the driver card. So I started looking at the driver card and I'm like, what could possibly be wrong? I've been working on this for the longest time and there hasn't been a problem. So I got out a magnifying glass and I discovered that there was a fine crack. On this trace, it was actually hidden in flux. It had been there for years and it finally failed on my watch. I fixed that trace system and that was it. That was the problem, and I went on my merry way to complete the repair of that 9090 dB. So the point is, you never know when something's going to fail, okay? So you always have to variac your amplifier while you're working at it. Don't give up using the variac. And even if you go out to buy a vintage amplifier, you will benefit by this information. Because if you go and buy some vintage amplifier and the seller says, well, gee, it worked 10 years ago, the last time I used it. Well, we've all heard that story. You take it home and it blows up your speakers. Well, you could have saved your speakers if you had at least booted up with a dim light bulb. You don't necessarily need to boot up an amplifier with a variac and a dim light bulb. You can use the poor man's method and just use a dim light bulb. And if the light bulb glows bright, you know you got a problem. You know you have to take it to a tech. So this technique has saved me a few times, and it will save you too. Thank you.